nanohub.org.
Online simulation and more for nanotechnology.
Welcome to the recitation series. So today I want to talk a little bit about BJTs, but I'll start out with just giving a brief screenshot here of NanoHub, the webpage. I hope you've been there. Hopefully you have already registered. We are all about modeling and simulation and data, and we have over 500 apps that make simulation tools really easily accessible. And they're real tools under the hood. And then we have also full-fledged tools that require some more expert usage. We have content staged that allows people to learn and teach. Those are somewhat assembled into simulation-powered curricula, and I'll talk about that a lot today. We also enable people to develop software in various platforms that we provide easy access to. And then if you develop software or tools or apps, you can then share and publish them on NanoHub as well. So that's the homepage of NanoHub. We've also created chipshub.org, which is really a group inside NanoHub. So nanohub/group/chipshub goes if you type chipshub.org. So here we highlight our open courseware. We have courses. There's actually over 170 courses. We highlight a few here. We have free textbooks that are new and provide a new view of electron transport and thermal transport. And we have full-fledged TCAD tools. So Silvaco is on the line here, and coming soon we will have Cadence and Synopsys tools, the whole tool suite also towards chips design. Today I'm going to focus on the effort here on immersive learning to enable students to learn devices in a more immersive fashion. So if you click here on semiconductor devices, you get to a page on NanoHub that has ABACUS. And ABACUS is, in a sense, a tool of tools. And that's what I've been highlighting in the last few weeks here in this recitation series, where in a standard course, you might start with crystals and then develop band structure models. Then you treat bulk semiconductors. Then you get into p-n junctions. And often people still teach BJTs. I do that too in my class, where it's really a back-to-back p-n junction. And you can study electron flow rather easily. And that's the topic of today's conversation. And then typically you close out the course with MOS capacitors and MOSFETs. So those are the next few recitations we still have lined up. And so here are some animations that highlight what ABACUS does. And each of these highlights here has also a sub-page, so to speak, in this wiki format. And here we highlight this BJT lab. And there's various exercises and operational descriptions that you can use in your class. So let me just launch this ABACUS tool. And that's now launching a virtual machine that is sitting on some server. And we are seeing the screen output of that machine. And here is a splash screen of ABACUS. And so here are, again, just some simple images of the devices we want to look at. You can also use a pull-down menu to peel them off from here. But you might as well just click on this link here. And what happens is it pulls up this BJT lab. Now, this BJT lab is actually powered by Padre, which is a full-fledged industrial strength simulation tool. And this tool actually did design transistors for Bell Labs. And but you can use this tool in a rather easy fashion. So this here is a simple textbook-like linear 1D BJT and NPN. You can do a PNP in the same form. And there's also a more realistic version like this, which has a structure like this, where it's a vertically stacked device, and you can specify more physical parameters that are relevant to more realistic structures. So let's go into an NPN where we started. And what you can do is you can modify the various lengths of this device. You can modify doping, dielectric constants. You can change the material. And you can change some other characteristics in the material, such as the minority carrier lifetimes. You can request certain aspects here on the Gummel plot that we will be looking at, and specifying various aspects of the output characteristics we want to calculate. So what might you teach in a class? So let me go over here and my PowerPoint, and I'm going to pull up just some slides of how I teach this BJT. So you have an NPN device. It's under bias. You have really two PN diodes here built in. And what you're doing is trying to get electrons across, and you do that by really controlling the base current here at this device. And that's the basic operation of a modern MOSFET as well, where you have a barrier and you control this barrier, and electrons flow, and they always flow at some leakage rate, and that rate is really determining the 60 millivolt per decade. And as you lower the barrier, more and more electrons flow, and eventually they saturate. That's sort of a pictorial view of the basic operation. Now the question is, how do you control this device? How do you optimize this device, etc.? So in a BJT, you have similar output characteristics, and what you write down is the Ebers-Moll equations that are quite well known. You have a current that is here, collector current that stems from these two junctions, the base and emitter junction, base emitter and the base collector junction, and they're just, here's the base collector term for the PN junction, and here is the base emitter term. And the base current has two components, again, current flowing from the base into the emitter, that's this term, and current flowing also here to the other side. Now, if we are reverse biasing this thing in the base collector junction, these components here that are being back injected are very small. So we can discard this term, and the same is true. There's not going to be holes flowing this way in this reverse bias. So we can eliminate those terms. We have two terms left, and basically the collector and the base current are dominated by this junction here, the base emitter junction. So when you do that, you have basically plot two of these currents. You plot the collector current, the base current, and basically your output is your current. You want this to be high with as little control as possible, and the ratio between these two is the current emitter gain beta. And these green terms here cancel out, so your gain can be approximated by all of these coefficients here. And what is in there? So you have some structural parameters, that's the base width and the emitter width. You have material properties with a diffusion coefficient for electrons and for holes. And then you have intrinsic carrier concentrations. So you can change these if you changed a different material, for example, that might point to heterojunctions. And you can modify the doping in these devices. And then you see plots like these in a textbook, and this happens to be from the Pierre textbook, where you say, okay, there's some non-idealities down here from recombination, and there's high-level injection from current crowding and others where it tapers off. So if you now, let's skip over this, if you now plot this beta, you basically see here in the middle, you have pretty high gain where these curves are roughly parallel. And then here below, the gain falters and becomes small, and also on the top here you're curving off and you're not getting as high of a gain. So what would you do if you had a tool and don't just want to cranking some abstract numbers? Let's play with a tool and see if we can design a little bit of a transistor. And so what you have here is the tool set. And let me go in and make this sort of a very plain vanilla equally doped NPN transistor. And maybe make a couple more points in the Gummel plot, maybe some 25 points. So what you see now, I'm running this tool. It's actually constructing an input deck, and this is a run I haven't done because I actually changed the number of the data points here in the Gummel plot. And it'll take a minute to run. So this is what you see is sort of the screen output that this industrial strength Padre tool dumps out. So things are happening in this simulation. So I really cranked up this number quite a bit. But it finished it. Now it's assembling all the outputs. And what do you get? So here you start out with an electron density and hole density. You end up with a common emitter output characteristic. So here's the collector current, and as you crank up the collector emitter bias, you see the typical characteristic. So now let's look at the Gummel plot here that we talked about. So this looks somewhat similar to this, right? But this is now for a more realistic device and you see that roughly here in the middle, these seem to run pretty parallel. And so if we read a number here, this is, so the ratio between these two looks like roughly maybe 1 order of magnitude, maybe 10. We can now look at the ratio, actually the beta. So here's the beta. It's roughly 10 as I eyeballed it. It's not quite linear as what the textbook describes. And here's the beta output. So in a textbook with these equations that we had here, right, the beta, we want to get a high amplification. So we have a couple of options and knobs we can play with. So we can, for example, increase the emitter doping, and we can reduce the base doping. So that should crank up this beta. So let's do that. So we can go in here and let's crank up the emitter doping. What? It's typed. Let's do this, 5E17. So it's going to assemble this input deck and run it. And this will take probably a minute. And as you normally, when I do these demos, I use the similar inputs or identical inputs. And what happens then, if somebody has run a simulation already, it'll pull that simulation from cache. So you don't actually compute truly the simulation. We just pull in the data. But I wanted to try out something new today. So you guys get to suffer and actually see the real demo, not just canned results. Yeah, this instant on helper is storing the results in the database. So now what I did is I increased the doping, right? It's no longer identical doping all the way across. You can kind of see it nicely on a log-log scale. And let's look at the Gummel plot here. So you see the two curves are going apart more. So here is, if I click the all button, I can compare these two. So this is the previous one. This is the second one, where I increased the emitter doping. I can just turn this off and flip in between. So as you as you increase the emitter doping, what are you doing? You're reducing the base current here more, and you're increasing, preventing more of the roll-off here on the high side, and overall your beta is increased. So let's look at the beta. And indeed, the beta is going closer to 1,000, and then it tapers off up here, and it's increased significantly over our original design, right? So now we can do the following. We can go in and say, let's, so where is this this drop-off coming from? So we can look at a little bit here at the band edge diagram under final bias. So here's our BJT. Let me just turn this thing off. So actually it might be good. So here, for the low current version, you see that there's some resistive drop here in the collector. If we crank up the current more, you actually see more resistive drop. You see that the band edge is dropping off at a higher slope. So if you want to avoid resistive drop, so you need to have more carriers available there. So you can't really mess around with the mobility much unless we change with the carrier lifetimes. So what you can do is increase the collector doping a little bit, and let's see what happens. If you have higher collector doping, you should be able to get a reduced potential drop in the collector. So we're running this again. It takes another minute. It's a little bit like watching paint dry, but actually sometimes it's good to see if the output comes back well. There could be error messages down here if things don't go so well. All right, so here now we have increased the doping here in the collector. You can see it on the log-logs plot. We had a higher doping here. And let's look at the beta. And here now, let's compare the twos. So here, as we cranked up the collector doping, we see a slightly roll-off to a higher currents here on the right-hand side. It's a little bit smoother here. And let's look at the band edge diagram at final bias. So what happened here at this higher doping, you can see that the bands in the collector are significantly flatter compared to the lower doping version. So finally, let's go in and maybe make this device even more heavily doped on the emitter, and let's see what happens and how we can improve this device. And while this is running, and hopefully we get a nice looking result, I wanted to see really here this where let's explore some of these non-idealities. I explored with you the non-ideality of high-level injection, meaning you have resistive drops. We just worked on that. That's why this current is peeling off. Let's see if we can play a little bit with carrier lifetimes here, and what happens down here at the lower current. And okay, so let's see. Switching back, result should be here. So now you can really see this is a N++ P N+ transistor with 3 different doping levels, and you can look at the Gummel plot now. Here you can actually see that this roll-off is quite relieved, and you can see the beta is now hitting over, getting close to 10,000. So we're really getting a very high current amplification out here for very high currents. So you can explore internal parameters of a device. You can look at various properties like electron and hole densities at final biases and at zero bias. You can look at the electric field, and you can look at recombination rates. And so there's a lot of recombination happening here in the base emitter region, and at higher doping, when you have at the lower doping, you have a lot of this recombination here. So let's play with this a little bit more and say, what if we actually assume that we have somehow some really long lifetimes? Just for argument's sake, let's make this 1 millisecond, and let's see what happens. Let's say we could make this happen and make it very clean, very small, very long lifetimes. So now I haven't done this, so I'm curious myself what this tool will do. And I want to do the other extreme, give it really short lifetimes and see how the performance should degrade. That would be my assumption right now. Okay, so doping didn't change. Let's look at the Gummel plot and look how straight this is now in terms of the output is about the same. It's the base current that is now significantly reduced. And let's look at the beta. Ooh, that seems a bit strange here. So now we have a much flatter beta here, up here. And this point, I'm not sure I would trust that data point. Same here. We seem to have some strange looking points down here. So, but now beta has become rather flat. So if you have this ideal material that has really long minority carrier lifetimes, you can get really nice performing transistors.
All right. Someone asked, where is BJTs used in current electronics?
Typically still in antennas, in antenna circuits. In your cell phone, there's probably an HBT in there, which is a heterojunction bipolar transistor. And in linear amplifiers, I believe, there's still BJTs in there. And in some very high speed, is there? Yeah, I'm not going to go out on them, but certainly on those items.
All right. Someone else asked, can you modify the code to simulate also hot electron tunnel transistors, which have similar operation principles to BJTs?
Not in this app, but in Padre and in Silvaco tools, you can certainly do that. So let me pull this up here. So Padre is the full-fledged tool that sits under the hood. And some 4,000 people have used it. But in order to use it, you've got to speak Padre. And so there is various devices in the default, and you can construct your device as you please in a classical simulator. The alternative I would offer is we have NanoHub tools. Well, let's do it this way. So Chips Hub, Silvaco. You can launch Silvaco, and there you can do all kinds of devices that are more complex, but you'd have to get used to the Silvaco environment. But this might have actually in the library examples. It might have a variety, the devices you're looking for. I hope that helps.
All right. Someone asked, can we make our own structure in this software?
In the app here that I demoed, you're confined to these four families of devices that are NPN linear, NPN discrete like this, and then PNP. In the Padre tool, you can design almost anything in 2 and 3D. But again, you'd have to speak Padre, or you do the same thing here in the Silvaco tool, where you can do, say, a nanowire type structure or a 2D structure, etc.
Okay, and someone asked, can you simulate graphene FETs in Padre?
No, that's that would be a different tool. We might have some graphene transistor tools on NanoHub. Yeah, here it is, the GFET tool. So here, here's a graphene-based field effect transistor tool. Okay, it's been used by 2,000 people.
All right, the next question, what kind of programming language is familiar to Padre?
So Padre, the source code, is actually written in this glorious language called Fortran, but users just need to speak this kind of input language, right? So where you have you need to speak meshing languages where you give different mesh specifications, doping, then solve for certain outputs. And there is a sort of a 200-page manual that goes with Padre. So if you go in this tool here, click about this tool, there should be a link to the Padre tutorial and the Padre manual. And you have to learn how to speak this specific language. Or, as I said, you can use the Silvaco. This is a commercial grade modern tool with a graphical user interface where you can start from examples, but then again, you also need to speak this kind of language, right?
All right, going back to the BJT simulator, is it possible to simulate at low temperatures, especially in freeze-out regime?
Yeah, so let's see what environmental variables we have exposed here. And I don't think we exposed temperature in this tool. In some of the tools, P-Junction-Lab, etc., we expose the temperature, but apparently not in this tool. It could be easily added as a parameter here, but it's not. When you run this, so I ran something else earlier. So in the this is actually the BJT input deck, and you can basically copy and paste this over. You can download it here, this output. You can basically copy and paste this code over into the Padre input deck, and you can set the temperature. And if it's not set, then it's defaulted to 300. But in the region, you can set temperature. Let me see if I see it. So, but in principle, this could be a feature request to want to model cold temperature BJTs. And I know, oh, here it is, right? So in principle, even the we could just expose this 300 Kelvin temperature, and we can expose the different recombination models, mobility models, and Auger recombination. We can have users turn those on and off, right, or change the temperature. So those would be cool enhancement to be made to this tool that you don't have to, code this up and copy and paste into Padre. But if you have research needs and need to just pursue that, that would be the way I would go about it. I would get to an input deck that looks close to what you're being interested in, and then I would go in and change the temperature. That's the short-term solution.
All right, great. I'll make a note of that request. And the next question, someone asked, what about the material library?
Yeah, so Padre knows about silicon germanium, gallium arsenide, the typical semiconductors. This tool predates graphene and 2D materials, so it'll know the standard semiconductors and has mobility models for it. And this is all drift diffusion. Padre is drift diffusion. If you wanted to have quantum transport with different materials, that's a different ball of wax. We can do that.
All right. Someone asked, can we simulate solar cells also?
In principle, yes. You can construct something in Padre. There's also a code called Adept. PB. So there's a whole group in NanoHub that is dedicated to photovoltaics, and they have tools that you might want to run.
All right. Someone asked, can we sweep some parameter such as doping thickness and plot the effect of its change on the current?
Yeah, so it's an extremely good question. So what you can do here is, which property was the question? I'm sorry.
Doping, thickness, and plot the effect of its change on the current.
Right, so the issue is, so yes, you can do it. For example, here, when you see these things here that have like a distribution to it, you can go in there and give it a just say uniform distribution where you vary this from say 1.1 to 1 micron to say 4 micron, and it will run a sweep of that parameter. And the problem is that we are used to looking at curves, right? Beta as a function of particular current. It's hard to draw distributions of this. So I haven't run this. This is called uncertainty quantification, where you basically sweep some parameters and it will say, well, how many simulations would you run? So this would lay over a grid of 5 runs in here, and it'll launch these 5 jobs for you and assemble outputs. But the output of a curve looks kind of funky. So in an ideal sense, you would look for a beta at a certain current, right? And look at beta as a function of sweep, or the maximum collector current at a certain bias. So you just home in on one current output, one number of current, so to speak, and then you can get a better distributions. So what it's doing right now, it's literally launching 5 simulations in the background and assembling this material. Again, uncertainty quantification and these sweeps are a bit easier when your output is just a single number, but we'll see what comes out here. But it's a really good question. I like it. Thank you.
All right, great. I might mispronounce this. Someone asked, are we able to simulate piezoelectric?
Piezoelectric devices. Maybe. So this here seems to be a summer project. One of my partners in Colombia has put together. So there's some piezoelectric simulations that may not be all you want. Let me go back. What else I find here? These look like lectures. No. So I don't see much other things. So not so useful here.
I did see one other question. Can we also simulate material surface modifications like bending of surfaces and plot the effect?
I am not sure. Simulate surface modification, bending of surfaces, and plot the effects. I would know how to do it in my Nemo code, but it's a bit of a stretch, quite literally. I don't know that we have a tool that does that, but there's 700 tools on NanoHub. I resort to Google, but I'm not familiar with those kind of models. But again, that doesn't mean it's not on NanoHub. Let me see. There's some lectures on NanoHub on surface modification. So yeah, it's kind of beyond the scope of this recitations. We'd have to dig in.
All right. I think that covers all the questions I see in the chat.
Thank you very much, everyone.